So, well, we're over with model-based approaches. So, as I said before, when you do have the model, when you do know the MDP, then everything is over, right? Because you can essentially describe by MDP your environment, and out of that you can specify the optimal policy. Everything is perfect, right? This is not really happening in practice. And don't kill me, I didn't teach you that because I wanted to just add content to the course. We really are going to use whatever we learned in this chapter. So it was not out of extra time I want to just add complication. No, we really are going to use that. But the fact is that we cannot really use it in the a statistically accurate way that we have done in this chapter. Okay? So in practice, what is going to happen is that we don't know the environment, and then we want to just come up with one remedy for that. We want to just design a mechanism that we can approximately do whatever we have done in chapter 2. So once again, the ultimate goal, just to find the optimal policy. We talked about this. We have two major challenges when it comes to practice. The first one is that we need to compute the values explicitly, and the other one is that we want to just run it on a real environment with a huge number of states. So that part 2, we have not arrived there yet. So we're going to get, after this chapter, we're going to get there. Okay? This is where we start the deep reinforcement learning. We are still in part 1, and in part 1, in the previous chapter, we talked about the model-based approaches, where we do know what is the environment, right? We can describe it using the MDP. Now, what we want to do in this part is we want to just do model-free approach, meaning that we assume that we don't know the MDP, right? When we are in one state, we really don't know what's going to happen to the next state. We cannot describe it, right? There is no mathematical formulation for that anymore. So, model-free methods are simply methods where we do not have the analytic model of the environment. And what we want to do, we want to just compute those value functions, action values, optimal policy, all of them. We want to compute them out of the samples we get from the environment. Now, this is getting more close to what you have in your mind about learning, right? Because you just see some samples from the environment and you want to decide how does this environment behave and what should I do as the optimal policy. So, this part, which I showed you initially, we are now over with it. So right now you know what is Bellman equation, right? And you do know that there are these two different algorithms, policy iteration, value iteration. These are the algorithms which are going to help you find the optimal policy, right? Now, what we want to do, we want to again do the same thing here. So we want to come up with one remedy to find at least approximately the value function, and out of that we formulate how we can find the optimal policy, right? And this is the first part of the course that we're going to do. So we're going to talk about the temporal difference and Monte-Carlo. These are the two approaches which are going to help us estimate the values when we don't have the MDP, right? And out of that, then we get into this idea. We can, for instance, do on-policy approach to estimate, and then we end up with one algorithm called SARSA. The other approach is that we work off policy, and then we're going to end up with Q-learning. So hopefully when you're over with this chapter, you have understanding of all of these terminologies here, okay? Cool. So now, let's start with the model-free approaches. First of all, everything you do in model-free is essentially generalized policy iteration. So you're going to start with one policy. You just try to find an evaluation for that policy. You improve that policy, and you keep on going, right? So this is the general approach you do also here. The only difference here is that when you want to evaluate your policy, you don't have these nice Bellman equations because you don't know what is the MDP. You cannot compute those expectations anymore, right? And you want to replace that thing, those expectations, with estimates you get out of your samples, okay? Cool. So this was the generalized policy iteration. So you start with one policy, you just evaluate that policy. Maybe you evaluate it in a generalized form. It means that you do not necessarily end up having the exact value of that policy. Maybe you terminate fast, early. Maybe you get an estimate which is not accurate, but it's okay, something like that. So you're going to find some sort of value out of it. This is not really the value of your policy anymore. It might be an estimate of it. That estimate might be initially completely detached from reality. You don't care. You keep on doing that, right? And since this algorithm is a quite solid algorithm, most of the time it's going to end us up with something useful. So you get this value, and then you put it inside the policy improvement. So you improve that policy using those bad estimates, for instance, that you have, and you keep on iterating that, right? So now, first approach that we can use in order to estimate the values without knowing the MDP is the idea of Monte-Carlo, right? So what is the Monte-Carlo approach? Say I have, like, I guess many of you know this, but just to give you a quick recap on what Monte Carlo is, let's consider a very, very simple example. So say you're in a lab, and in your lab you have one particular device, right? And this device is connected to a signal generator, and at the output of this guy, you're seeing some output, right? Each time you turn on that signal generator, some random signal comes into the device, and then you see only the output of that device. You can measure that one. If you are in a lab and you want to know what is the average output of this guy, what you're going to do, you're going to run this signal generator multiple times, right? And each time you see one, you're going to record all of those outputs, and then you average them, right? So this is the way that you do it. So if the device is the simple function f, and x is what is coming out of the random signal generator, then this output y is random because x is random, right? And the thing that you want to know is that you want to know what is the expected value of this device when random signal goes in it. So eventually what you do in what you need to do, if you know the distribution of the signal generator, you need to compute this expectation, right? But in practice, you cannot do it because you don't know the distribution of that signal, right? And how the device works, right? The only thing that you can do, you can only sample from your device, right? So meaning that each time you turn on the signal generator, your measuring monitor is showing you some value, right? And you just record those values and you average it. This is what you do in the lab. And this is basically what we call it Monte Carlo method, right? So you're going to sample a bunch of samples, y1 to yk, k different times you do the experiment, and then you average those k different samples. This is going to be an estimate of the mean value. So what is the exact mean value? The exact mean value is this guy, right? The expectation, which is taken over the data distribution, right? Or the signal distribution, right? This is the exact value you're looking for. But you cannot find it because you don't know that distribution, right? The thing that you do, you just do this one, right? What you get, this mu hat, this is not exactly mu, right? This is close to mu, hopefully, right? So sometimes when you do the experiment, it just lands somewhere after, like larger than mu, sometimes smaller than mu, somewhere around it, right? Now, if you want to reduce this variation around mu, what should you do? You just use more number of samples, right? The more samples you have, the better your estimate is going to be, right? Do you know what is the reason? Law of large number or the central limit theorem. Both of them is the same thing, right? So the reason is basically because of central limit theorem or law of large numbers. So if you have these k different samples and they are just randomly coming from same distribution, which you don't know, right? You don't know what is the distribution of y, and you don't care. The thing that you know is that each time you run that signal generator, this is coming from same distribution, right? Independently. Now you have k different samples independently from the same distribution, and then if you just average them, so if you compute this guy, right? The thing that you're going to see when this k gets larger and larger, this is going to converge to a Gaussian random variable, right? the mean value of this Gaussian random variable is exactly what you are trying to estimate. The variance of it is some variance, which is the variance of your sampling or whatever, or the regional data coming, divided by the number of samples you have, right? The more samples you get, the smaller your variance gets, right? Meaning that if I am trying to find one specific value, and say that value is 1, but I am sampling. The first time I sample, I get 2, right? The second time I sample, I get 0, right? Each of them is an estimator for that 1, right? But 2 is very far away, 0 is very far away. But when I average them, it's now 1, right? So if you do it like with 5 samples, you just vary it somewhere around 1 with one window, which is proportional to 1 over 5, right? If you do it with 50 samples, then the window is going to shrink. It's going to be 1 over 50, and so on, right? So you are just going to get closer and closer to what you want. And this is the reason that this is working. This is what we call it Monte-Carlo approach. Now, what I want you to have in mind from now on is that when you are doing this approach, when you are sampling from something, and you don't know the distribution, it's okay. I want to think of this guy, mu hat, to be what you want plus some error. And this error is a kind of, you can think of a Gaussian noise, right? So it's not necessarily Gaussian, but like if k is large enough, this is approximately Gaussian, right? You can think of it as a kind of error. So this is the true thing that you want with a bit of error around it, right? And this error is going to shrink, gets smaller and smaller the more and more data samples you have. Okay? So this is an important thing. Just keep it in mind because it's going to make all understanding of this chapter much easier for you. Not only this chapter, in the entire course. Because at the end of the day, we are not able to compute any of those expectations we have in the Bellman equation. We are going to always approximate it by this approach, right? Everybody's cool? Questions? Now, do you know what is Monte Carlo word coming from? The name Monte Carlo? Yes? Game show? Close? So it's not Monte or Carlo. These are not people. Monte Carlo was a casino in Monaco. Do you know where is Monaco? It's a tiny country below France, right? It's a kingdom. And then I think the name of the mathematician who developed this is Ulam. He was in the Manhattan Project, but he was a statistician. And he had an uncle. He was having, the uncle had a gambling habit. And he was going to casino, this Monte Carlo casino, doing gambling. And then he said, oh, you have lots of data. Maybe I can estimate something out of it. He came out with this Monte Carlo approach, right? It's quite an old thing. But Monte Carlo, I mean, it's not fair because Monte Carlo is not the one who developed it. It's just the casino. But yeah, I mean, it got the name, right? So, anyways, so now the idea is that you can use this idea of Monte Carlo to estimate the expectations you want in your Bellman equation or anything like when you want to evaluate your value function. The easiest way is that you first forget about the whole Bellman equation that we had. You just start with the definition. So what is the definition of the value in one particular state? Is the expected future return, right? So what you can do, you can start in one particular state, right? Play as much as you can, right? Each time you play, you just make it an episode, right? Till you end, right? And then you see what is the future return, right? This is one sample. You take another sample, sample. If you keep on sampling, then you're going to have lots of samples. You average them. This is approximately the value of that particular state, right? So you can simply do this with this very simple idea. So you start with one particular state, S, and then you want to know what is the value of this state if you play with the particular policy, pi, right? So you can play one episode, right? You start with that at that state, and then you play with your policy till you end up with the terminal state, right? This is one episode, right? So you start at this state, you play policy pi. When you are at the terminal state, then it's over, right? Say t time steps, and then you finish, right? This is one sample that you got. You can just compute the future return of that particular episode, right? So you see that I started with this state. What was the first reward I collected? What is the next one? What is the one after? And so on till the very end, right? And then you add all of them up in the specific form with the discount factor as we define. This is one sample future return, right? If you keep on doing this for k different episodes, then you're going to have k different samples, right? And the value of the policy at this particular state can be estimated. You see the hat here, right? Can be estimated by the average of these sample returns, right? Everybody's cool? So you got the idea? So this is the easiest way you can think of estimating your value function out of the data, right? So what you can think, if you want to think in terms of the backup diagram, and I just put it here because later on we are going to use it a couple of times, so just to get used to it. So this was the backup diagram that we talked about. We start from one particular state, right? Then if we play with the policy, we can go, depending on the policy, we can go in one of the actions, right? And then when we go in that action, again, in this new action, the environment is going to take us to a new state, right? In that new state, you are again going to take one action based on policy, and you go to the new action, and then the environment is going to change the state, and so on, right? And what you are going to do, if you know the MDP, it means that you really know the probability of all these edges, right? So you do really know how, when you do one action, how this environment is going to change to the next policy, right? But now you don't know them. You don't know the probabilities on these edges. What you do, you just sample from it, right? You start in your state, and then you do one action. So you just play with policy. The policy tells you do this action, right? You do that action, you get into this particular action. Now, upon doing that action, the environment is going to take you to the terminal state, right? This is one sample that you got. Maybe next time when you do it, it does not end you immediately with the terminal state. Next time you play with your policy, you do another action because maybe your policy is random, right? And then doing that action, it's going to end you with another state, right? It's not the terminal state. Again, in that state, you are going to play with your policy. You're going to do one action, and after doing that action, you end up with the terminal one, right? And you keep on doing, so you're sampling from branches of this tree, right? And when you end up with one terminal state, then you can add up whatever you have collected. This is the sample reward, the return that you get. You average it. You are approximating or estimating the value function. So this is the algorithm, quite simple. So what I'm doing here in this algorithm, I want to just evaluate the value of one particular policy and at one particular state. And you should pay attention very much. I'm computing the value in one single state, right? If I want to do it for all the states, I should do the same process for every single state, right? Right? So I could have n different states. This n could be very, very large. This algorithm should run over all of them, right? So I'm now talking only about one state, right? Everybody's clear, right? So I have this particular state S. I have the policy pi. Now I want to know what is the value of this policy at this particular state. And then the point is that I don't know the MDP. What should I do? I start with value 0 initially, and then I start sampling, right? So I go inside this loop. I start with this particular state S, right? If I start with a particular state S here, then I keep on playing with my policy. And playing with your policy, you're doing one action, go to the next state, another action to the next state, so on, till you end up with the terminal state, right? This is going to be one episode. And then once you finish this episode, you are going to collect your sample return, and then you are going to add it up to your value function, right? You are going to average all the samples that you had, and you're going to take this as the estimate of your value function at the state S. Everybody's clear? Questions? No question? So, now, one thing, if I want to just estimate the value of my policy at one particular state, with this algorithm that I showed you here, when do I have the value? Can I do it after every sampling, or should I wait till the samples are over? I need to wait till samples are over, right? Because for every single sample I get one sample G, I need to collect all of them, and then I average them, right? So it means that this algorithm is going to give me the value after k different samples, right? So I need to play k times, see the values, and update it, right? But one thing that you might tell me, and this is very valid, is that, okay, if I do like, say for example, k is 100, right? But after the 10th trial, I have maybe a bad estimate, but still I have an estimate, right? Can't I use it at this point, and then when I get the new sample, I improve it? Well, we can do it, right? This is what we call it online averaging. So right now in this very dummy algorithm that I showed you, you need to wait till all the k episodes are over, but you maybe say that, okay, if my few first episodes are over, I can use the sample returns to compute one bad estimate, right? And gradually, each time I get more samples, one new sample, I can update it to get better sample, right? Estimator, right? So this is what the idea of online averaging is. This is not a very, very complicated thing. The key point is that the thing that you are averaging right now is this one, right? You are collecting k different sample returns, and then you average them, right? Now, what you can do, you can open up this summation, right? I can write it down in this form. So I have k different samples, right? I add up the first k minus 1, and I keep the last one out of the summation. Okay? Everybody's cool? Right? Now, this first guy that you see on top, so I'm going to copy everything the other side. So 1 over k is still there. I have this, this bracket, and gk is here, right? Everything is here as before. The only thing that I'm dropping right now is this summation, right? Everybody's cool? Okay, now if I get this summation and I divide it by 1 minus k minus 1, this guy is the estimate that I get with k minus 1 samples, right? Correct? Right? Then what's going to be that summation? Is going to be k minus 1 times this estimate, right? Everybody's cool? Now, which guy is the better estimate? Can you tell me? Which guy is the better estimate? Eta k or eta k minus 1? Eta k, right? Because it has more samples, right? Okay, but anyways, now I can simply write down this summation to be k minus 1 times eta k minus 1. I replace it here. Okay? Everybody's cool? Now, just do a bit of math. So first you multiply it, so it's going to be in this form. Then I'm going to take eta k out, eta k minus 1 out, and then I just factorize 1 over k. So it's going to be in this form, right? Everybody's cool? So your new estimate eta k can be written as your previous estimate plus 1 over k times new samples minus previous estimate, right? This is what we call it incremental averaging or online averaging, because here you don't really need to wait for all the samples to be over, right? You have your first sample, you have one estimate. You get your second sample, you're going to update that estimate, right? You have your third sample, again you update, and so on, right? Okay, so this is what we call it online averaging, and simply you just do this, right? So every single time, your new estimate is going to be your previous estimate plus 1 over k times this delta. And what is delta? Is your new sample minus previous estimate, right? Everybody's cool? Yeah.
You're still like replaying the episode, right?
You are still replaying, right? But when you are over with one episode, you have one estimate, right? And you again replay, you improve your estimate.
Okay, what's the difference then between this and just
You cannot, I mean, here you're not updating, like, don't mistake. Here you're, I mean, this one that you get is not in between, before the loop is over. This is not the right estimate, right? So this is not the case. Like, if I have k equal by 1, then in the first iteration, my estimate is exactly the sample I got, right? In the second estimate, I get the first sample plus the second sample divided by 2. In the third one, first plus second plus third divided by 3. But here what you are getting is every time you just multiply by 1 by 3, and then you add it, right? So this is not the same thing at that one, right? So right, maybe it was not a good idea here. Maybe I should have put this out of the loop. So maybe next time I do it like that. But here, this is not an online update, because in between, before you're over with the whole k episodes, this value that you get is not the right estimate, right? Okay, so everybody's cool? Everybody got this idea? So eventually, you start one episode. Whatever you get, this is the only sample you have. This is the only estimate, right? Second time, you get a new episode. You get a new sample. And also update your previous estimate, right? And you can keep on doing it as much as you want, right? So we have basically not changed anything in the whole mechanism. The only change is that we are just, each time we're collecting one new estimate, right? Now, one thing that we typically do is that we typically drop that 1 over k and we replace it with something like alpha. Now, this alpha is a general factor, right? It could be 1 over k. If it is 1 over k, it simply means that my average is first sample plus second sample plus third sample till the last one divided by k, right? This is the case. But you might average things with non-uniform weights, right? You can do it as well. Like, for example, you have one estimate, which you know this is a very good estimate. You have one other estimate, which you know is a poor estimate, right? What you do? You're going to get this one. Maybe you multiply it with 0.9. You get your poor estimate. You multiply it with 0.1, and you add them up. You're still averaging them, because 0.9 plus 0.1 is 1, right? But the only difference is that you are giving less weight to the poor estimate as compared to the good estimate, right? And this is what you can do in general. So you really don't need to consider it to be 1 over k. You can think of it to be one specific alpha. Now, this alpha could be constant. It could scale with k. If you set it to be exactly 1 over k, then this is basically what you're doing linear averaging, right? So you are linearly or uniformly weighting your weights in your approximation, in your estimation. But if you keep it constant, so if you put, for example, alpha to be 0.1, then you can do the math and you see that you're basically doing the averaging with geometric coefficients. Like, one of them is alpha, the other one is proportional to alpha squared, alpha cubic, and so on, right? And then if you sum all of them up, at the end it could be 1 when alpha is smaller than 1, right? So you keep always alpha smaller than 1. This is important. But if you keep it fixed, this is still going to work. And typically we keep it fixed. Okay? Questions? No question? So if I want to use this online averaging in my algorithm, so my algorithm is now exactly as before. Again, I am going into one loop. And inside this loop, every single iteration, every single time I'm just sampling one episode. And this episode is giving me one sample return, right? Now, the way that I update, I simply update whatever I had as the previous update plus alpha difference, right? And this is a new update, right? You keep on doing this as much as you want. Everybody's clear? Questions? No question? So you got the idea of Monte-Carlo with online averaging, right? Okay, cool. So now, next thing that you might see in this approach that we have done is that what I'm doing right now, I am just doing sampling one episode, right? And when I sample that episode, I start with my state, I go on all the way towards the end of trajectory, but I use this whole trajectory to estimate the value of the starting state, right? Is it optimal, or can I use this trajectory better? Can I use this? Yes, go ahead. Perfect, right? So you can do that as well, right? If I get from a state 1 to a state 2, right? And after that I go on, right? Now the sample return for state 1 is whatever I collected after it, right? What about the sample state 2? State 2, whatever I collect after that as well is another sample, right? That sample is the sample return for state 2, right? So I am not actually with one episode, with one trajectory, I am not sampling just one sample return. I am sampling all the sample returns whose state is seen in between, right? Everybody's cool? So what I can do, I can say, okay, maybe I have started at S0. Of course, whatever I collect after is going to give me a sample return for a state S0, right? But of course, R2 towards the end is giving me the sample return for S1, right? That's right, right? I can forget about whatever had been before. I started at S1. I played with my policy. I ended at the terminal state, right? It's again another sample, right? If I go ST minus 1, I immediately start with the terminal state. This is, again, another sample, right? Everybody's cool? So this is not just one single sample return. It is indeed T different sample returns, right? And I can use all of those T's to update the corresponding states, right? So I could say the value of S0, whatever S0 is, that the value of that state could get updated, right? The value of S1, whatever that guy is, can get updated, and so on to the value of ST minus 1, right? Because for every single of them, I have one new sample. You see it? Questions? Okay, so this is going to be the case where I am just sampling with one episode. And look at this algorithm. I am not writing down S anymore, right? Inside that algorithm. So I'm not talking about one particular stage, right? Because when I just sample from the environment, the complete trajectory, I have lots of state happening in between, right? And I can update all of them, right? Everybody's cool? You see that? Okay, so what I'm going to do, I'm going to take the episode, k different episode. Starting with the first episode, I just sample one complete trajectory towards the end, right? Now, I start with saying that the sample return is 0 when I am at the terminal state, right? When I consider terminal state ST, ST is the terminal state, right? And at that terminal state, the sample return is 0, obvious, because the terminal state. All samples are 0, right? Now, I go one step back. So I say, what about ST minus 1? Well, at time, now this is small t, think of it to be t minus 1. The value of this state, whatever that guy is, t minus 1, is going to get updated. Whatever it was before, plus alpha times the difference, right? How I compute this g here? What is the g when I am at t minus 1? What is the sample return for st minus 1? What is it? No, sample return when you are at this state st minus 1. RT, right? So RT you collect after that 0, right? That is RT, right? So it's going to be RT. So for st minus 1, this g is RT, right? What about st minus 2? What is going to be? RT minus 1 plus, for now I assume that the discount factor is 1. RT minus 1 plus RT, right? What if I am at one particular time t? It's going to be R. If I am at one particular time t, it's going to be RT plus 1, plus 2, and so on, right? But that RT plus 2, 3, and so on is eventually the sample that I have computed previous time, right? So each time you can write it down in this form, right? Everybody sees that? So you start with g being 0, you're at terminal state, right? The sample return for t minus 1 is rt plus 0, right? The sample return for rt minus 2 is rt minus 1 plus whatever I collected before, right? rt minus 3 is going to be, st minus 3 is going to be rt minus 2 plus rt minus 1 plus rt. But rt minus 1 and rt, sum of them is the previous g, right? So each time you start from very end, you start by saying that the sample return is 0, obvious at the terminal state. And each time, whatever the return I see, I'm going to add up with the previous sample return, right? And this is a new sample return for that particular state. Now I can go ahead and update every single of those states that I see in between, right? Everybody's clear? Questions? Now, if I do one trajectory, how many states could potentially get updated? How many states? What is the most complicated, like most, say, diverse case? S0 is one state. S1 is different from S0, right? So you start from one state, you go to another state, right? S2 is different from S1 and S0, and so on. Each time you see a new state. If that happens, how many states you see in between? T different states, right? So one of these trajectories is going to update T different states, right? Potentially. But it might be that you start from one stage, you go again to the same state, right? You hit the wall, you're back, right? Then you are collecting two samples of the same stage, right? Everybody sees that? You're clear? Right? But in the most ideal case, each trajectory is going to give you is going to go over T different states, right? And if you do K different episodes, and each time you're starting from one different state, you're going over all completely different states, then you're going to have K times T different updates, right? Everybody sees that, right? Clear? Yeah.
So let's say you started at S0 and then after a few steps you went back to S0.
Yeah.
The first sample for S0, would it be the return after you hit the terminal state?
No. You have two samples for S0. One of them is the one, like you say I start from, say, cell 0. And I play, I again get to cell 0, and then I terminate, right? One of the samples is the second one. The other one is the complete one, right? It's because, like, think of the random walk, right, on the grid. So if I start here, I randomly walk. In one of the samples, I just walk exactly, get to the terminal, right? Once again, I just play around, and then I get to that one, right? Both of them are samples, right? And what is your value is the average of all of them, right? So you need to have both of them. Questions? No question? Okay, so now, looking at this guy, if you start doing this algorithm, right, you can go ahead and sample your environment, right? So I take one trajectory, I update, all right? And then if you think of that table I used to show in the example in the previous chapter, you start with all the values in the table, think of your environment as the grid world, then every single state is one of the cells, right? And you want to write down the value, estimate the value of all these cells, right? Every time that you do a trajectory, a couple of them gets updated, right? Right? Everybody's clear? So if you think about this guy in form of a grid world, then you're going to have such an environment, right? This is the whole environment that you have. Right? So you start with all of the values being 0 because simply you have had no samples at all, right? Everybody is 0, right? But now you start to play, right? You start maybe from this cell, and then you come here, you come here, you come to the terminal stage, right? And when you do that, this guy, and this guy are going to get updated, right? Maybe once again you start here, and then you come again here, and then you come here, you come here, you come here, you come here, right? Anyone in between is going to get updated, right? Everybody's clear? Now, you keep on doing this process. So each time you just sample a new trajectory. You randomly start somewhere. You play with your policy. You go over a bunch of cells till you end, right? Again, you start here, you play, you end, right? You keep on doing this, and each time you're updating, right? Now, if I play a lot of times, significantly large number of times, such that I'm pretty sure each of these cells have been seen, say, 100 times, okay? Then the one that I am computing, the estimate that I am computing, is the average of 100 sample returns for that cell, right? And that is a fair approximation, right? A fair estimate, right? So if I can make sure that I am playing enough number of times such that I am meeting every single state in my environment for a large number of trials, right? Then this average, which I get, this estimate that I get out of the Monte-Carlo approach, is a good approximation, right? And this is what we have here. So eventually this Monte-Carlo approach could converge if you just sample enough number of times. And how much this enough means, this simply depends on the number of states you have in your environment, right? If you have an environment with a few states, then when you play 100 times, probably you see all of them enough number of times, right? But if you have a huge environment, then 100 is not enough, right? Probably you need to play thousands of times or even more, right? But you can formulate it concretely here. So you could say that, say, CKS is the number of times, so I have k different episodes, I play k different times, k different trajectories, right? And I am just counting the number of times that I am seeing the particular state S, right? So this state S is maybe this guy, right? This guy is a state S. If this guy, this one, say this guy is a state S, right? If I play 2 times, like the one I showed you here, both times I am seeing this guy, right? So it's going to be 2, right? But the number of times that I see this guy in these 2 trials is 0, right? I have never seen it, right? I had no sample. So CKS is the number of times that you're going to see in the state, you're going to see a state S in your K trials. And if you have this property that every single state that you have in your environment, all these cells here, all of them are seen enough number of times. Like you play K so large, and your sampling process is designed a way that when you just play infinite number of times, each is being number of times, right? If that happens, then you could say that the value that you're estimating using Monte-Carlo is converging to the exact one, and that makes sense, right? Because I get to this cell infinite number of times, I have infinite samples, I average those samples, this is going to converge based on law of large number to the exact expectation, right? So there's no magic in this theorem here. It's basically law of large number. I just formulated it more concretely. Questions? No question? So if that is the result, so it says that the value function is going to be, the estimate is going to be value function. So if that simple approach is solving the problem, why do we have deep reinforcement learning? Any idea? What is the trouble in this result? What? Number of states, n, right? So if you really want to see all the states enough number of times, right, this k should be definitely larger than the number of states you have, right? Right? Because each time you play, if you are very lucky and always you pass through different states, at the end you need to have seen all of them at least once, right? And then the result is not even telling you at least one. It says like enough, right? Now, the number of states that a chess game has is, I told you, 10 to power. You check the first assignment, right? 10 to power 100 was 120 was Shannon estimate. Then there was reduction. 10 to power 40, right? Just I give you discount 10 to power 30, right? 10 to power 30 states you have, how many samples you want, at least 10 to the power 30, right? And now you compute how much time you need, more than the age of universe you're going to need in order to sample that much of samples, right? Impossible, right? So this result is nice. This is giving you a concrete way to estimate your value function without using the exact MDP. But the key point is that computation is not feasible, right? And this is why we gradually try to play around with it. We just do some modification to it to make it more and more feasible. And eventually we're going to get at some point to the deep reinforcement learning where we actually confirm that, I mean, we accept that we can do nothing about the number of states, so we just need to estimate this whole value function. Like this estimate, we should find it using a network, okay? But there we're going to get soon. Questions? No question? Okay, so I think the time, oh, let me see. Oh, okay, I have 3 minutes, so 3 minutes only. And this is going to be less than 3 minutes. So if you get into the dummy grid world and you start with the random policy, now you can use the Bellman equation. And for the random policy, you're going to see that the values are like this. Okay? This is the terminal state. It's going to be 0. The other ones, just write down the Bellman equation, do the calculation. You're going to end up with this value, right? And then this is a very small environment, right? You just need a few samples. So if you start, like this is the optimal value function. So at the state 0, it is 0. At a state, at state 1 and 2, it's minus 4.5. And at state 3 is minus 6, right? For this random policy, right? But you start playing with the random policy in this environment, and you don't use the MDP. Okay? If you start with everything being 0, and you play a couple of times, you're going to see something like this, right? So it's getting close to the numbers, but it's just jiggling around it, right? But you need to just keep on playing. And if you keep on playing, eventually at some point you're going to converge very close to that exact value. Everybody's clear?